Hi everyone, I'm Remi, founder of Inco. So what we're building is what we call the Universal Confidential Computing Network. So today, all the L1, L2s have one thing in common, is that they are completely transparent databases. So we do believe there needs to be a minimum confidentiality necessary for mass adoption. So a couple examples. Today, if you were actually to onboard billions of people in crypto, it would actually be social chaos. The reason why is everyone can see everyone's balances. If you do payroll, you can see how much everyone's making. Enterprises and institutions are still having a hard time entering the space. They've tried private blockchains in the past, like Hyperledger or 3Corda. It's not quite the same because these are essentially private servers, and then you don't get to interoperate. You also don't have access to the same amount of liquidity and also user base. And then lastly, there are just a lot of use cases that wouldn't make sense without confidentiality. So think of the card games, private voting, blind auctions. So the cryptography we utilize is called FHE. So by show of hands, who have heard of this term before? Well, I guess it's PT days, but the idea is that you can encrypt data and compute on top of it without having to decrypt. So if you're non-technical, imagine being able to encrypt a picture and still be able to modify this picture without seeing what it is. And by the time you decrypt, now you have a filter. So FHE is not a new concept. It's been discussed since the 70s. Before, it was mostly a wild idea, like what if we could encrypt data, but also compute on top of it. The first breakthrough was back in 1999 with the Palier crypto system, where it was proven that you can do simple homomorphic encryption operations, mostly additions. The challenge with FHE is really around this concept of noise management. So when you compute over ciphertext, you have this noise accumulation. Back in 2009, the second breakthrough here is really around this concept of bootstrapping that allows you to basically reduce the noise. So you can think of it a way to keep the noise in check. But this process was still very slow until recently. Another breakthrough was around this idea of programmable bootstrapping. It's essentially a fast table lookup that allows you to do basically bootstrapping in a very efficient manner in tens of milliseconds. So FHE, what makes FHE really unique is sort of the decoupling between compute and decryption. So you can think of FHE being compute bound, and then MPC decryption being more networking bound. So here, the way to scale FHE really is through hardware acceleration, so similar to ZK. And a lot of these teams, so there are dozens of teams working on the hardware accelerations. They're all coming out next year and the year after. And their specialized FPGAs are just more optimized to do polynomial multiplications and things that can re-accelerate FHE compute. So what makes FHE really stand out compared to a more legacy solution around that are ZK-based? It's really around this idea of composability. So actually, I had a brief conversation with Cooper earlier. I think we have a slightly different definition of composability. What I mean by composability is actually composability over encrypted states. So obviously, Aztec Aleo does have composability, but that's, I guess, over public states. So slight nuance here. And what makes FHE a little bit interesting here is the form factor. So with FHE, you encrypt data into ciphertext. It's actually very similar to a blockchain data because you get to store a hidden data directly on chain. With ZK, the challenge here is that you have a different form factor that you need a prover, you need a verifier. So a lot of the state managements are very different, right? You store the encrypted data off-chain in ZK. You need a prover to coordinate the states. And then you do a state transition and then commit on-chain, right? With FHE, when you have the encrypted data on-chain, what you get is this permissionless way to interact with a smart contract. So any user could directly interact with a smart contract that's a private state and compute on top of it. So imagine if we all predict the price of Bitcoin in a hidden manner, we can all submit our ciphertext, and then we can still compute the average directly with the smart contract. So it's really this idea of shared private states, and it's quite easy to use for any use cases that involves multiple parties. I would say that's the major differentiation. So what we're building here today is what we think is the missing layer in the blockchain stack. So you have folks like Celestia building DA as a layer. What we're building really is this confidential computing layer. And so the way I see this is very similar to the early internet, where everything was plain text. You could only do academic research back in the days because everything was transparent. You really needed SSL to exist to start encrypting information, so you can encrypt credit cards, payments, and then bring in businesses, right? So with this, we do believe that this is the next frontier. It's the next frontier because you can enable novel use cases that wouldn't be possible before. You can also bring in new types of crowds that are more institutional because of this encryption layer. And just like how Chainlink enabled a new DeFi ecosystem to unfold over the years, with this idea of private state on chain, you can also basically build new things that wouldn't be possible before. And so we think this is a big market because a lot of these things do touch payments, real assets, a lot of DeFi applications. So you can think of Inco, we are a layer 1 blockchain. There are a couple of reasons why we chose this form factor, but from a high level, ZK today, FHE today is very difficult to make it verifiable. So the bootstrapping step is the most costly step today. There are researchers that have proven that you can do it, right? It will take 20 minutes to do a single bootstrap. So not quite feasible or practical today. There are two other options. One is more of an optimistic way. So we can think of some kind of fraud proof. And then lastly, it's basically through consensus. So economic security plus consensus, where you have to basically recompute the work and then cross-compare. So Inco essentially is this layer that acts on top of existing blockchains, like layer 1, layer 2s. We provide basically verifiable compute through consensus. We also store your ciphertext. And more importantly, we get this property of instant finality. And so a lot of people actually don't think about instant finality in this space, why it's so important. It's important because if you have a system that can rework or that's optimistic, anything you decrypt, that information is leaked. Or imagine if you start unwrapping assets. If you rework, it wouldn't quite make sense, right? Unwrapping assets is basically bridging. So with Inco, you at least get this guarantee, a couple properties, like I said, so replicated compute, where you have guarantee on the compute, replicated storage, and also this property of instant finality. So one feedback that we often get is, ultimately, are we just trusting your MPC network, right? It is somewhat true because ultimately, by decoupling FHE compute and decryption, the decryption network ultimately has the ability to decrypt things, right? And the challenge with MPC is, like a lot of the previous speaker also mentioned, is you are network bound. So scaling MPC is going to be quite challenging. It cannot scale up and down like typical blockchains. And if you scale, into a large network, then you're really just networking bound, right? But ultimately, because of this, we opted into this more modular approach where, because we're able to decouple compute from decryption, you can actually choose different types of MPCs that could be based in different jurisdictions, but also different technologies. You can also bring in your own keys, right? Because you're able to decouple decryption and compute. So it's very similar to today, like TLS, or if you want to secure your website, you will basically get a certificate, and then you run basically this client-server relationship, right? So you can imagine choosing your own key systems or bringing your own key systems here. So we made Inco very intuitive. So the idea is you get to write this FHE code directly on top of existing blockchains. For Solidity developers, this has been, I would say, the biggest advantage, which is the simplicity of writing code. You basically just read and write code like you would normally do in Solidity. You just have additional encrypted states and then additional operations on top of these encrypted states. Not only this, now you get to basically utilize the existing ecosystems, their user base, their existing TVL, just build any application you have in mind very easily. So this is more about this idea of as an L1, don't you have the cold start problem where your market cap is lower, it's not going to be as secure. So with EigenLayer, what we do here is this idea of dual staking. It's a very novel concept. The idea is you can do staking both using Inco, but also a native asset like ETH, right? And so what you get from this is you're solving two problems. So one is typically layer ones because they have higher volatility, they have to give out higher inflation rates to compensate for the inventory risk that a lot of the stakers have, right? So by leveraging more mature asset class, you basically reduce the inflation rate that you have to give out. And second, you also get more economic security since day one that you get to rent very cheaply. So we are compatible with existing Ethereum tooling, so Hardhat, MetaMask, Remix. It's very easy to build because of it. A couple use cases. So what can you really build with this, right? I like to give this example because it's an example that I would say most developers will be familiar with, just a basic ERC20. So here, as you can see, we have an encrypted type called EUINT. So your ERC20 is really just a mapping of address to EUINT. If you do an ERC20 transfer, you're just doing an FHE addition and an FHE subtraction, right, to update your balance and the recipient's balance. And so this experience is actually very similar to Venmo, where on chain, underneath the scan, you can see person A has some money to person B. The flow of funds is public. It's only the amount that's hidden. Another example is, isn't it crazy to think that like there's no poker today in crypto, being in our industry? So the reason why there's no poker is because this is a hidden information game. This game would not make sense. You wouldn't be able to bluff unless you're able to hide your cards, right? So this is where, using FHE, we're also able to generate on-chain randomness to generate these cards. And so the idea is, you can have your plaintext logic to coordinate, like, people depositing money, calling, folding, and then you can use FHE to basically generate these cards that only you can view, essentially. And this is something that Chainlink would now be able to support because they provide plaintext VRF. And there are other companies who have provided, hidden randomness, such as Secret Network. But what we're doing here is a different approach. We're utilizing FHE here. Another game I like to present is this fully on-chain Mafia game. It's a multiplayer game. Here you generate the role fully on-chain. The reason why it's very easy to build this using FHE is because this is a coordination game. You need this idea of shared private state to coordinate states. So if I were to do a hidden move on the player, it's much, much easier and straightforward to build a logic when you have this coordination layer that's the blockchain itself. Another example I like to give is, I think this is a very unique concept that doesn't exist today. So today when you do DIDs, you will KYC with a third party, and they will send you a soulbound token that says, okay, are you over 18? Are you accredited? It's quite static and dynamic and quite inconvenient because all this information is revealed, right? With FHE, you get to do comparisons, not only just operations, but also comparisons. So what this really means is that I get to store your date of birth or credit score directly on chain. And then I can also selectively reveal insights by doing comparisons. So maybe for a casino dApp, I just want you to know I'm over 18 and nothing else, right? So just as an example, if you do tfhe.gt, meaning greater than, this is what I mean. You can actually do a comparison, and then all you have to do is decrypt sort of like the insight, right? Whether it's true or false. And so you can imagine having a money market, a polygon that basically interacts with this DID layer, queries insights, and then based on that, you can whitelist the user. And in the case of a credit score, this could also change over time, right? So that's why we call this a dynamic DID. It's actually very mimicking what we have in Web 2, where it's similar to Google Auth. If you connect to an application, you can say, I want you to access my calendar, but not my Google Drive. But that information could change, right? Like your contact list could change, your calendar could change. So a lot of what we're doing here is actually just bringing in what we're familiar with in Web 2 to Web 3. So FHE today, can support pretty much all the operations that we have in Solidity that people are familiar with. You can do divisions, multiplications, additions, also comparisons. So it's really up to the developer themselves to really explore this, new greenfield of, opportunities. And I would say historically, because of the fact that all the public blockchains are completely transparent, not a lot of folks have spent too much time thinking about designing around, around privacy. And so obviously there are challenges around designing around privacy. So if you want to build things around DeFi, you have to think about information leakage, right? You have to maybe consider utilizing things like differential privacy. So it is not easy by any means if you want to build more complex tools. But it is quite of an interesting area that we're quite excited about. So if you're interested in building anything, obviously feel free to reach out to us. We're a very use case centric firm, so we like to provide feedback in your ideas. I also have a list of use cases that you can check out here. So here are docs, and I'm happy to answer any questions.